Salam and welcome everyone. So today we're going to be working on the question on the screen that says the work function of a metallic cesium is 2.14 eV. Calculate the kinetic energy and the speed of electrons ejected by light of wavelength 300 nanometers and by light of wavelength 700 nanometers. I'm going to start with this first question if I go to solve the second question. I just wanted to mention this is a question from chapter 7A in the Atkins Physical Chemistry 11th edition textbook, and it requires some steps. And please pay as much attention as possible because I'll be bringing in concepts as well as other knowledge. It's not just a direct calculation. You still need to know some information in order for you to successfully do this calculation. So the work function of a metallic cesium is 2.17 eV. Now, we're going to write out all that we're given and then we would go ahead in solving it. So work function with the symbol is just simply 2.14 eV, okay? Then we're told to calculate the kinetic energy, which is EK, okay? And then the speed of light, which is just speed of electrons, sorry, which is just V, ejected by the light of wavelength this. So wavelength is just simply 300 nanometers. So that's basically it. So the formula, whenever you have questions like this that you're actually supposed to use to solve this question, is simply EK, which is kinetic energy, is equal to H times frequency minus the work function. So kinetic energy is HV. HV, by the way, is just simply the energy of each photon. Okay? Energy of photon. That's what HV is. And then, yeah, HV is equal to energy of photon. So they could just have simply written change in E, energy of photon here, but we're just going to substitute it for H and V because usually they're not even going to give you the energy of photon. You tend to calculate it. And the second and the most important thing in this question is a term called work function. Okay. Some of you may be hearing it for the first time today. For those of you who you're not hearing it for the first time, kudos to you. That means you've been reading your textbook. But work function simply is the minimum energy. I want to talk a little bit more about the concept first. Energy required to remove or eject an electron from the surface of a solid material. From the surface of a solid material. That is it. Work function is the minimum energy required to remove or to eject an electron from the surface of a solid material. So that is what work function is. And here we're giving work function to be 2.1 eV. Because we're supposed to get the kinetic energy in terms of joules, there's something you have to do. You have to um, go from EV to joules. So 1 EV is equal to 1.602 times 10 raised to the power of negative 19 joules. So 2.14 EV is going to equal X. Simply, you're going to cross multiply. X is just equal to 1.602 times 2.14, okay, times 10 raised to the power of negative 19 joules. So when you do that, you have the new value for work function to be equal to 3.42828 times 10 raised to the power of negative 19 joules. So this is basically the answer. So now that we successfully determined the work function, then we have to determine what V is. We already know what V is. It's frequency. Frequency is simply C divided by lambda because C is equal to lambda times frequency or wavelength times frequency. Hence, the value for frequency is just simply C divided by lambda, where C is the speed of light at 2.998 times 10 to the power of 8 meter per second. So that is basically what that is. So now we already know what to substitute V for. So now our new value for EK, which is the kinetic energy, is simply going to be, okay, H C divided by lambda, because we're substituting the value for V to be C divided by lambda minus the work function. So that is basically, this is it. This is it right here. So all we have to do right now is just simply substitute. So kinetic energy EK is equal to 6.626 times 10 raised to the power of negative 34 joule seconds. That's the Planck's constant, okay? Times the speed of light, 2.998 times 10 raised to the power of 8 meter per second, divided by lambda, which is just simply 300 times 10 raised to the power of negative 9 meters, okay? Minus the work function. We solved the work function to get 3.428 times 10 raised to the power of negative 19 joules. Forgot to add joules here. Joules, joules, because we converted from EV to joules. So minus 3.42828 times 10 raised to the power of negative 19 joules. So you cancel out joules here. I'm sorry, you cancel out seconds here, cancel out seconds here, cancel out meters here, cancel out meters here. So you end up with EK is equal to 6.626 times 10 raised to the power of negative 34 times 2.998 times 10 raised to the power 8 divided by 300 times 10 raised to the power of negative 9 will end up giving you 6.62158 times 10 raised to the power of negative 19 minus 3.42 times, sorry, minus 3.428 times 10 raised to the power of negative 19. Joules here, of course, and joules here. Let's never forget our units. So when you do this and you put in your calculator, you end up getting 3.1933 times 10 raised to the power of negative 19 joules. So we know as chemists, our work is still not done. We have to put our work in the proper number of significant figures, which is just simply EK. So kinetic energy ends up becoming 3.19 times 10 raised to the power of negative 19 joules. So this is the kinetic energy of the electrons that are ejected by the wavelength of 300 nanometers. So we're going to go on to solve the speed of electron next, and we're going to be using the formula for kinetic energy, which is EK is equal to what? Half mv squared. We have EK to be kinetic energy, m to be the mass, and v to be the velocity. Next, we rearrange the formula. EK is equal to half mv squared in order for us to solve in terms of v. Don't forget, v is what we're actually supposed to solve for, right? The speed of electrons ejected. So anyways, we now have, if you want to write this in terms of v, we're just going to say 2ek is equals to mv squared, and v squared ends up just becoming 2ek divided by m. V, which is the velocity that we're solving for, becomes the square root of 2ek, or 2e sub k, is equals to, sorry, divided by m. So this is going to be the formula that we are going to actually use to determine the speed of electrons at that wavelength. So we've successfully, found the kinetic energy. So we can just basically substitute all the values we have. We already know what the value for the kinetic energy is. Alhamdulillah, we've gotten that one correctly. Then we also know that we have to divide by m. M is equals to the mass of electron. But they did not give us the mass of electron in this question. But if you've studied chemistry, general chemistry and introduction to chemistry, as well as even some topics in physics, then you're supposed to know the mass of an electron is equal to 9.1094 times 10 raised to the power of negative 31 kilograms. And I want to quickly mention something, right? The electron that we're talking about, that we're saying that, the mass is this. Even if you don't know it offhand, in this physical chemistry thermodynamics textbook, Atkins physical chemistry textbook, at the back of the page, you can see the mass of the electron. So that would just be mass of electron is 9.1094 times 10 to the power of negative 31. And that's what we're going to substitute into the equation. So V is equals to the square root of 2 times E sub K is just simply 3.1933 times 10 raised to the power of negative 19. Okay, we already know The kinetic energy is 3.1933 times 10 to the power of negative 19 joules. Now, I want to quickly mention something so everyone's on the same page. Joules, okay, is the same thing as kilogram, meters squared, per second squared, because joule is basically the unit for energy. And energy is simply equal to force times distance. Force is just simply mass times acceleration, okay, times distance. So if you want to break down the units of each one of this information, you would be able to end up getting kilogram meters squared per second squared. For example, now the unit of what they call it, the unit of mass is kilogram, the units of acceleration is meter per second squared, and the unit of distance is simply meters. So that's how you get kilogram meter per second squared. I'm saying all of this information to say that we cannot just substitute joules in this. We have to put it in the SI unit form. So it's going to be, the energy is no longer 3.1933 times 10 to the power of negative 19 joules. We're going to just put kilogram meter squared per second squared divided by 9.1094 times 10 to the power of negative 31 kilograms. So that's basically what it is here. So that's basically it. So you cancel out the kilograms. You do the substitution up top. So 2 times 3.1933 times 10 to the power of negative 19 is the same thing as 6.3866 times 10 raised to the power of negative 19 meters squared per second squared divided by 9.1094 times 10 raised to the power of negative 31. So V is equal to 7.010999 times 10 raised to the power of 11, okay, meters squared per second squared. That's another thing over here. So then you end up with V. When you take the square root of 7.010999 times 10 to the power of times 10 raised to the power of 11 meters squared per second squared, what you end up with is just simply 8.373171 times 10 raised to the power of 5. The square root of meter squared is just simply meter, and the square root of second squared is just simply second. So this is going to be the speed, but we are also chemists and we cannot leave our work in this number of significant figures. The raw values are too many, so we have to put in the proper number of significant figures. So when we go back up top to see, we see that all what we've been given is in three sig figs. Even the rounded up value of the kinetic energy is in three sig figs. So we're going to put our final answer in three sig figs. This is in three sig figs. So this one ends up becoming, the velocity ends up becoming, or speed, 8.37 times 10 raised to the power of 5 meter per second. So this is the speed of electrons ejected. So yeah, that's basically the answer. If you have any questions, suggestions, concerns, you can put in comment section. So that is the first half of the question. We have another question that says for us to work on this with 700 nanometers, right? So the second question involves us solving for 700 nanometers, but everything else is the same. So the first thing you have to know is the wavelength is 700 times 10 raised to the power of negative 9 meters. Okay. The work function is also 2.14 eV, which we can simply rewrite to be, the work function is also equal to 3.42828 times 10 raised to the power of negative 19 joules. So that's that as well. We also know that our Planck's constant is 6.626 times 10 raised to the power of negative 34, okay, joules seconds. And our frequency is just simply going to be our speed of light divided by lambda. By the way, I'm just rewriting all of this just because we've been talking about this already. So the formula that we're going to use to determine the kinetic energy for 700 nanometers is going to be simply EK, okay, is equal to HV minus the work function. Or we can rewrite this as EK is going to equal H, and then we substitute V to equal C divided by lambda. So that will be HC divided by lambda minus the work function. So this is what we're going to use. This beautiful thing here is what we're going to use. This is what we're going to use. So of course, we just simply substitute. We have the wavelength, we have the Planck's constant, we have the what's it called again? We have next we also have the work function, and we also know what the value for C is. C is just 2.998 times 10 to the power of 8 meter per second. So E sub K, we're just going to substitute. E sub K is simply 6.626 times 10 to the power of negative 34 joules seconds times 2.998 times 10 raised to the power of 8 meter per second divided by lambda. That's 700 times 10 raised to the power of negative 9 meters minus the work function 3.42828 times 10 raised to the power of negative 19 joules. Perfect. So that's it. That is it. So of course we cancel out this one right here, cancel out this one right here, cancel out the meters, also the meters, just like you just did for the seconds. So we end up with E sub K is equal to 6.626 times 10 to the power of negative 34 times 2.998 times 10 to the power of 8 divided by 700 times 10 to the power of negative 9. That information there, when you put in your calculator, you end up getting 2.8378 times 10 to the power of negative 19 joules minus 3.42828 times 10 raised to the power of negative 19 joules. Now, when you do E sub K, you end up getting negative 5.9048 times 10 raised to the power of negative 20 joules. Now, this is the answer to the kinetic energy. Now, you're going to be wondering, okay, well, this is looking good so far. No, it is not, actually. I wanted to quickly explain this for you. First of all, sometimes whenever we solve questions, we get carried away with the solutions without actually thinking about the concepts that we're learning. Kinetic energy cannot be a negative value. It has to be positive because kinetic energy is the energy of motion. So negative motion is the same thing as no movement. So you cannot have a kinetic energy of a negative value. Now, we can calculate it and think about it in theory that is negative. So remember, the question is actually asking you, the work function of a metallic cesium is 2.14 eV. Calculate the kinetic energy and the speed of electrons ejected by the light of wavelength, in this case 700 nanometers. In order for it to have kinetic energy, meaning the electrons ejected to have kinetic energy, the work function actually has to be less than the energy of the photons. Do you understand what I'm saying? Like it has to basically be less. So what I'm trying to say is it is not possible here for the work function to be greater than this energy value hv or hc divided by lambda, because in order for there to be kinetic energy and in order for electrons to be ejected from the surface of the cesium metal material, the work function has to be less than the energy that of hv. Because it is not less and because it is more, it would just mean that a negative kinetic energy means no electrons were ejected, because the energy that is needed to overcome it and the minimum energy required in order for it to be able to be ejected is actually less than the work function. So the work function is more, and it's not going to work that way. So basically, since there is no photo ejection, meaning the light did not hit the metal to cause it to what is to call it, or let's just put it this way, since the energy of the light that is hitting the metal in order for it to eject the electrons is less, so the light energy is less, so the energy of photons that are coming in to hit the metal. So just think about it this way: this is a cesium here, you need the photon or the light energy to be hitting it. Now, that one is less than the work function. Because it is less, you're not going to have a situation where electrons will be emitted because it's just much lesser. So you have a situation where there's negative kinetic energy, aka the electrons are not ejected, they just sit still on the surface of cesium. So that is what I'm trying to explain. And of course, since there's no photo ejection occurring, there is no speed of electrons ejected to be calculated. Since there is no photoejection, meaning the light causing the electrons to be ejected. Since there is no photoejection of electrons, okay, there cannot be kinetic energy. Don't forget the kinetic energy that we calculated that is negative is just telling you that, like, it's negative in theory. You can calculate it, but it cannot actually happen in reality. There cannot be kinetic energy and there cannot be speed. Like, what is the speed of something that doesn't move? Zero. There is no real speed. So the speed is just basically zero, you know? So that's basically how you think about it. You cannot calculate the speed of something that doesn't move. There cannot be kinetic energy and there cannot be speed of electrons to be calculated. So that is just basically the answer to this question. There are going to be questions like this. I do a very similar question like this on this channel as well. And I think that you guys should please watch that. I also wanted to ask you that if you have any suggestions, observations, concerns, or just requests on how you think this channel can be improved and what you like to see on my channel. My intention is to grow the channel so that STEM students can have a safe space online where the questions that they are being asked or whatever they're doing personally to study to succeed in the STEM field, that they can feel comfortable, and my channel can be a source of tutoring and mentorship as they go through their journey. So whatever you think can be helpful to make this channel grow and that will be valuable to you guys and for you to gain the knowledge that you're seeking, please also always put that in the comment section before you leave. I would also appreciate a subscribe. I also wanted to mention that if you're a student struggling in any of your STEM related courses, whether you're in middle school, high school, or college, I am the tutor for you. I help students succeed in all their STEM related courses. And if you would like me to be your tutor, please just email me at shahabitutoring@gmail.com. I wish everyone all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.